Okay, let's do a couple more examples of different types. Now this one you actually had a homework question similar to it. This is a curling stone. Okay, so here's my curling stone. And it says it's released so that it travels from the hog line, which is where you let it go, to the center of the button. And this distance, delta D, is 34.5 meters. Okay, and it stops on the button. So the VF is 0. We don't know what the VI is. What is, oh, actually we do. It's released with the speed of 5 meters per second. And the question wants to know, what is the coefficient of friction if it stops, coefficient of kinetic friction if it stops right on the button. So from these three pieces of information, we can get our acceleration. So we know that if you have delta D, VF, VI, and you want A, use your VF squared is equal to VI squared plus 2A delta D equation and rearrange for A. Isn't it great? Like, kinematics never goes away. That's why I wanted to make sure that you knew those equations so well, because they always come back up. It stops, so VF is 0. So A is equal to negative bracket 5 meters per second squared over 2 times 34.5 meters. So on the bottom is 69, on the top is negative 25. And when you do this, you get negative 0.3623 meters per second squared. And the negative means opposing motion, slowing down, whichever one you want to put in here. Okay, so we have our acceleration. So now we can do our sum of our forces. So we have Fg going down, we have Fn going up, and when you release the curling stone, there is nothing going forward. Right? You do not slide down the ice and continue to push it. So there's no forward force, just the backward one. So sum of the forces in the y is equal to MAY, and the curling stone is not floating into the air, nor sinking through the floor. So AY is 0, so Fn minus Fg equals 0. So Fn equals Fg equals mg, but we don't know m. We weren't given it. So even if you wanted to, you couldn't get a number here. So you're going to have to, your choices are give up or go to some of the forces in the x and hope that something works out. So in the x, some of the forces is equal to max. What are the forces? There's just friction, and it's acting backward. So I'm going to put a negative in for it, is equal to max. Problem is I don't know m and I don't know friction. But I do know that friction is equal to mu Fn. And so where friction is, I'm going to fill in mu Fn. So minus mu Fn is equal to max. And where Fn is, I can fill in mg. So negative mu mg equals max. And lo and behold, the m's cancel and I can solve for a. So, no, what am I solving for? I could solve for mu. So, negative mu is equal to ax over g. So, a was negative 0.3623 meters per second squared, and we're going to divide that by 9.81 meters per second squared. And when we do, we end up the negative and negative cancel, and you end up getting 0.0369 for your mu. Okay? So that is example 7. Example 8. Now we're going to get to the exciting ones. And I just added 7 in there because of the ones you did the last set. I was worried maybe you wanted to see a new one. Another one. So example 8. This one's going to be exciting because there's a little itsy bitsy twist to it. So we have a toboggan, it's 75 kilograms, and it's being pulled across a level field with a force of 400 newtons acting upward at an angle. So here's my force here. It's 400 newtons acting upward at an angle of 60 degrees, so with the horizontal. So it has a component in the x direction and a component in the y direction. Okay, before we talk about those, let's keep going though. Coefficient of friction between the ground and the toboggan is 0.2, and it wants to know what is the acceleration. So if we add in our other forces, we have an an Fg going down, an Fn going up, and friction going backward. Okay, so you're going to start now with this force F, okay, that's at an angle. It's not pulling in the x or y, but it has a component in both, and we can find them. If you look at the x component, so just draw, remember, any vector is really just a hypotenuse that's looking for its legs, so draw its legs around it, and those are the components. And so the x component is the adjacent side, so it's going to be cosine. So cosine of 60 is going to equal fx over 400 newtons. So fx is going to equal 400 newtons cos of 60. Cos of 60 is just 0.5, so fx is 200 newtons. And fy is the opposite side, so it's sine. So sine 60 is equal to fy over 400 newtons. Bring the 400 up. Fy is equal to 400 newtons sine of 60. Sine of 60 is 0.866 times 400, 346.41 newtons. And once you find the components, then it's like this F is not even here anymore. And now we can go to some of the forces in the y direction. And here's where it gets interesting. This toboggan is still not floating up into the air, still not sinking through the ground, so MAY is still 0. But this time, we have an Fn, we have an Fg, and we have an Fy. So there's an extra force in the y direction. No longer is Fn just going to be equal to Fg. Fg is going down, Fy is going up. You're always trying to solve for Fn, so take the other two over. So Fn will equal Fg minus Fy. Fn will equal, Fg is just mg, so 75 kilograms times 9.81 meters per second squared minus this 346.41 newtons that you just found a minute ago. And Fn ends up being 389.34 newtons. Okay? You have Fn and you have mu, so now you can find friction. FFR is equal to mu Fn. So friction is equal to 0.2 times this 389.34 newtons. So friction is equal to 77.868 newtons. And now you can go to your last step, sum of the forces in the x direction. In the x direction, what's pulling it forward? Just Fx. What's pulling it backward? Friction. And that's equal to max. And you're trying to solve for a, so divide both sides by m. So notice, nowhere does this lone f go in. Its components go in the appropriate sides, but the F isn't pulling in the x direction or the y direction, and so it doesn't show up on its own in the x direction or y direction. So Fx, 200 newtons, minus 77.868 newtons, divided by 75 kilograms. And you get an AX to be 1.6284 meters per second squared. Okay? So that's why I wanted you to keep doing the sum of the forces in the y, even though you kept getting Fn equals Fg. It is not always, but doing the sum of the forces in the y will always work so that you can find out what Fn is equal to. So now we have one more example to do. We're going to run out of time and we'll come back to it in the next video. Okay?